Now today we will see analysis of frames by using moment distribution method. So we have already seen how to analyze beams, indeterminate beams by using moment distribution methods, then how to construct bending moment diagrams, shear force diagrams, etc. So we have already seen this various types of frames in slope deflection method earlier. I had already given to you the definition as well as various examples of non-sway type and sway type frames. Now there are two types of frames, non-sway and sway type. That is lateral, only we are considering the lateral sway of the frame, not the vertical. And when the lateral sway of frame will occur, when the frame is symmetrical with respect to loading, geometry, then support conditions, and columns being not identical. Columns being identical, then there will not be lateral sway of the frame. Such frames are called non-sway type frame. Means if there is a symmetry in all these parameters, then lateral sway will not occur, and we call these frames as the non-sway type frame. If any of this parameter is unsymmetrical, means if loading is unsymmetrical, then geometry as far as vertical central axis is considered, if geometry of the frame is not symmetrical, then support conditions are not symmetrical, columns are not identical, means height of both the columns must be same, the supports of the columns must be same, as well as the moment of inertia of the column must be same. So if this is not identical, if this is not symmetrical, then there will be a lateral sway of frame, and the frame is called sway type frame. If the given frame is a sway type frame, then we have to take more care while solving the problem by using moment distribution method. So in case of slope deflection method, what happens? Delta, that is sway of the frame, was an additional unknown. But here in case of moment distribution method, if sway occurs, due to sway additional moments gets developed, and then we have to analyze the frame in a different way. Before we start solving the problems on sway type frame, let's see first few non-sway type problems. So let's consider first problem. Say for this simple frame, this is a simple type of frame subjected to, say, load UDL 6 kilonewton per meter. So A, B, C, D. So this is a simple frame actually. See, this end is fixed, and such type of frame there will not be any sway. So this is a non-sway type frame. So this is a non-sway type frame. If the given frame is a non-sway type frame, then the analysis of frame is carried out exactly similar to continuous beam. There is no change in the procedure. Now that means the first step is to find out fixed end moments. Let's calculate fixed end moments. So MFAB equal to left end minus WL square by 12. So you find out this. Then MFBA right end, it is plus WL square by 12, and at B for overhang we know we get the final moment directly. MBC equal to minus this 6 into 2 square upon 2. So this is minus 12 kilonewton meter. So this, you just do the calculations and find out this. I think this is minus 8 and plus 8. So these are the fixed end moments. Then second step, distribution factor. So distribution factor at the joint P are to be calculated. So let's calculate the distribution factors at joint B. So K, and we know that the distribution factor for overhang KBC is always 0. That means KBA is equal to stiffness of BA that is A is fixed, 4 EI upon L, that is 4 divided by 4 EI by L plus stiffness of BD. So D is fixed, again 4 EI upon 5. So this gives us stiffness of BA. Similarly, stiffness of BD, that is distribution factor for BD towards D at B towards D, equal to, say, this 1 minus this. So this you will get 0.56. So this is 1 minus 0.56 equal to 0.44, because total is 1 and for orang it is 0. Total distribution factor should be 1. So we have calculated distribution factors. Now next step, let's prepare a moment distribution table. Let's prepare a moment distribution table. So non-sway frames are analyzed exactly similar to the continuous beam. So analysis of non-sway frame is easy. Now prepare a moment distribution table here. Say this is A, then joint B you take here, and then this is D. So over the B we have to write down distribution factors. Say this is A, this end is, say, D, so this will be BA, then central is BC, and this is BD. So this way you prepare the moment distribution table for this frame. So this is 0.56, BC 0, BD 0.44. So distribution factors that we have calculated, enter the values, and fixed end moment at their appropriate places. -8, this is +8, for orang this is -12, here it is 0, 0, no moments. So you can write down this step as fixed end moments. Now next we have to see whether there is any simple support orang. Orang is there, no doubt, BC, but now directly we can balance the joint B. So to balance, find out unbalanced moment, that is +12 -8. You will get unbalanced moment +4. So balanced moment is equal to -4. So this -4, that is balanced moment, multiplied by 0.56, you write here. This -12, sorry, this is minus, this is plus, this is minus, and this is plus. So the balanced moment is positive. That balanced moment multiplied by 0.56. So you write here, this comes out to be 2.24. Here it is 0. Then 4 multiplied by 0.44, so 1.76. So this step is called balancing. So this step is called balancing or distribution of moments. We are using distribution theorem. Next, carryover. So balancing carryover, balancing carryover. So carryover to next support by half value with same sign. So this is 1.12. And here, now see, this cannot be carried over because, no, this D is fixed. So this is to be carried over. Half of this is 0.88. 0.88. Now carryover, next step balancing, again carryover, balancing. These two steps repeats. Now here, there is no unbalanced moment left. So there is no unbalanced moment left. So problem ends automatically. So now just calculate the final moments. So calculate the final. This gives us final moments. So final moments, just take summation under each of the support. So this will be minus 6.88. This is minus 12. This is plus 1.76, plus 0.88, and this is 10.24. This is positive, 10.24. Our problem is over. So we have calculated end moments by moment distribution, and in one cycle only it completes. Now next is to draw BMD. So to plot the BMD, so what we have to do, so let's show this is anti-clockwise, means this is 6.88. This is clockwise, again this is anti-clockwise, and this is 1.76 is clockwise, and this is again clockwise. So this is 0.88, this is 1.76, and this is 12, this is 10.24. 10.24. Now just enter the values according to their signs. Now to construct BMD, let's take a frame as a reference line. So you take this frame as a reference line. Over this, let's construct bending moment diagram. Now due to UDL, first so for AB, WL square by 8 due to UDL, so this is the ordinate, and this ordinate WL square by 8, so this is 12. This is 12. Then due to loading, diagram is over, just due to the end moments. So this is anti-clockwise. So draw BMD on tension side due to end moment. So this produces, if you take the section here, this produces tension upward. This also produces tension upward. So for AB, these two are to be drawn upward side, or both the arrows are downward, draw ordinate upward. 6.88 and 10 point. So this is, and this is 6 point. So this 10 point, this is 6.88. Again, this is also produces tension upward. And finally here it is 0. So this is 12, and this is 10.24. This is 10.24 is this point, this is 12. And then here, so this is 1.76. And this side, tension is on this side. So this is 0.88, 1.76. So I'll draw the ordinates perpendicular to the member, opposite to the arrows. Arrow here downward, this is downward, upward. Then this arrows, say this is downward, ordinate is upward. This is towards right, ordinate towards left. This is towards left, ordinate towards right. This also you can remember. And your resultant diagram is this. The resultant diagram is shown by shaded area. This represents the final BMD. So this is negative, this is positive, negative. And you decide one sign convention, positive, negative. So this is BMD. So let's consider the next problem. We will just go fast because we have already done the practice for preparing moment distribution table and calculating fixed end moment distribution factors, etc. So I want to solve more number of problems. And you practice these problems at home. The same problems you first solve completely, and then you solve the problems from books or from old question papers and do the practice accordingly. So next problem, let's take down. Again, we take a simple frame. Say here it is fixed, this vertical member. So fixed again, and here there is a hinge. Here there is a hinge, or maybe sometimes roller is given. So concentrated load is acting here. UDL is on this, and there is one central load. So this loading, this is 2 meter, this is 2 meter, this length is 3 meter, this is 2 meter, this is 3 meter, load, this is 12 kilonewton, and this is 3 kilonewton per meter. So A, B, C, D. No doubt we can develop such number of problems, but why I am taking particular problems, because I know the answers for this and we can complete the problem up to BMD. So we can manufacture such types of hundreds of problems just by taking the loading, support conditions, etc. Then this is 2I, moment of inertia. Here moment of inertia I, here moment of inertia I. So moment of inertia is also different. So next, so as usual, the first step is to calculate fixed end moments. So do it fast, little bit fast, fixed end moments, because now you have the sufficient practice for this. MFAB equal to minus WAB square by L square. You find out this. Then MFBA equal to plus WS square B upon L square, because this is eccentric load. Then MFBC equal to minus WL square by 12. Then MFCB plus WL square by 12. Then MFDB is left. So first you take DB. This is minus WL upon 8. And then MFBD, this is right hand plus WL by 8, so this is positive. So you find out, you do the calculations, find out all these fixed end moments. So now I will directly enter these values in the table only. So I think MFAB is minus 8.64 kilonewton meter, or you can write down these values. BA is plus 5.76. Then this is 2.25. MFBC minus 2.25, and this is plus 2.25, and DB is minus 5, and this is plus 5. So these are the fixed end moments. Okay. Now distribution factors. Let's find out distribution factors. So K, so second step, distribution factor K. So let's consider joint B. So KBA equal to stiffness of BA divided by total stiffness at the joint B, that is stiffness of BA plus stiffness of BC plus stiffness of BD. So stiffness of BA, this is A is fixed. For A, value of I is 2I divided by L is 5. This divided by 4A 2I 5 plus. Now stiffness of BC, C is hinge, 3EI, value of I is I, divided by 3 plus, this is 4EI divided by 4. And now you find out this. So BA, this comes out to be 0.44. So this is 0.44. Then KBC you can find out. So stiffness of BC, 3EI divided by 3. Then this total stiffness you write down here. So total you write down here, and this gives us 0.28. Then last KBD equal to 1 minus 0.44 minus 0.28. Again you will get 0.28, because total sum of distribution factor at the joint must be equal to 1. So this gives us 0.28. Now after calculating, see, already I have told you that this is the problem of 3 steps only. So finding out fixed end moments, distribution factors, and third, prepare the moment distribution table. That's all. In moment distribution table, you will get the final moments. In moment distribution table, you will get the final moments. And then we can construct bending moment diagram. So here, now I will tell you one more way, alternate way for preparing this moment distribution table, because already we have learned that how to prepare a moment distribution table for a continuous beam, and even for frame also the same can be used. But suppose at a joint, if number of members are more than 3 or more than 3, then it is always better to prepare the table in a different way. This table is slightly difficult to understand, but this is the most general type of table and applicable to any type of problem. So here the steps have to be written on the left hand side or left hand column. So joint, first you enter the joint, say joint A, then we have to enter member here, second row member. From A only one member is emerging, that is AB. Then next joint, you write joint B. From B we have 3 members, BA, BC, BD. So you take BA here. Sequence you can take any, that doesn't matter. BC you take here, and then BD. So 3 members are connecting at joint B, and sequence you can take as per your convenience. Then joint C, only one member, CB, and joint D, one member only, that is DB, or from D, DB. And here do not show the inclined arrows for carryover, so you have to understand properly, and then only you can use this table. But this is the universal type of table, applicable for any type of problem. Then after member, then you write down the distribution factors. You write down distribution factors. Now distribution factors, say I will write down by blue color, say mark a line here, then distribution factors. So we have calculated distribution factors 0.44 here, BC 0.28 and BD 0.28. So these are the distribution factors. Now fixed end moments. Next step, fixed end moment. So this table is also very systematic table. So now joints, members, distribution factors, and our calculated fixed end moments. This is minus 8.64, then 5.76, this is positive, minus 2.25 negative, then this is BD is positive, CB is positive 2.25, and DB is negative minus 5. So the calculated moments are entered. Now from here onwards, we are following our usual procedure. Procedure is same, only the way of preparing the table is different, slightly different. So here next, just look at the supports. A is fixed, nothing is to be done for A. D is also fixed. That means we can start directly moment distribution. But the support C is a hinge. And what is the procedure? Whenever there is a hinge or say overhang, for overhang we have to balance and carry over first. For hinge we have to release the bending moment at hinge support, and then we have to obtain the initial fixed end moments. Now here that means the next step is release of C and carryover. This is our usual step, release of C and carryover. Where CB? Where is CB? CB is here. Means apply equal and opposite moment. Release means we have to apply equal and opposite moment and make it 0. Then whenever we apply external moment, so we have to carry over the same with half value, same sign. So CB, read the reverse, CB, BC, it is here. So minus 1.125, minus 1.125, half of this with same sign. So this step is over. Now next is initial moment. Let's obtain initial moment. So we are following our usual, this table you can use even for continuous beams also. So initial double line, initial fixed end moments. I have marked double line because I want summation here. So that's why I marked a double line. Later on, while taking final summation, we must take the summation below this double line only, under each of the supports. So let's take the summation. This is minus 8.64, 5.76, and this is minus 3.375, this is 5, this is 0, and this is minus 5. Now balancing of joint B. Let's balance. Balancing or distribution theorem or balancing. Let's find out unbalanced moment. How we will find out unbalanced moment at B? That is 5.76 minus 3.375 and plus 5. So you calculate the unbalanced moment. So this resultant is the unbalanced moment, and that unbalanced moment multiplied by 0.44. Whatever you get here, I think this is plus, this is also plus. So you will get positive. So this is negative. This, whatever is this value, so minus. So that means you will get here minus, you will get here minus, you will get here minus. Because our unbalanced moment is negative. Unbalanced is positive. We have to make equal to 0. That we have to balance the joint, means the balanced moment should be equal and opposite, and that is negative. And that moment is multiplied by 0.44. Here you will get 3.249. Here you will get 2.067 and 2.067. And next step is carryover. So you complete this. Cycle is completed here, and next is carryover. Now carryover by half value with same sign. That means BA is to be carried over to AB. Here it is, and this should be minus 1.624. Then BC cannot be carried over because C is simple support. BD is to be carried over to DB, and this is minus with half value 1.033. So now the process carryover step is over. Next is balancing, but we don't have any bending moment here, unbalanced bending moment here. That means our problem is over automatically. So here complete the problem. And these moments are called final moments. These moments are called final moments. And whenever we take final, mark a double line, just for our convenience. So take the summation between these double lines, initial moments, because already we have taken summation here. And this gives us, this will be minus 10.264, and this will be plus 2.511, and this is minus 5.442, and BD 2.953, CB 0, and DB 6.033. But this is minus 6.033 anti-clockwise, and this is clockwise plus, this is anti-clockwise. So now with this you show the moments on the frame. So this is